today we'll basically finish the mathematical preparations. Then on Friday we'll do spectral geometry, and then we can do general relativity. Okay, so remember the curvature map is defined in this way. It maps 3 tangent vectors into a tangent vector by doing this operation here. These covariant derivatives acting on that tangent vector gives us a tangent vector. And for this curvature map, we found Bianchi identities. Remember, Bianchi identities are very useful equations which are built into the differential geometric framework. They are not Euler-Lagrange equations. You're not deriving them from an action because they would hold no matter what the action is of the theory. There was no choice when Einstein developed general relativity. The Bianchi identities had to hold anyway. Still, it's good to know them and to use them. So here's the first Bianchi identity. It says that the cyclic sum of this term, so you get 3 terms, r of psi eta nu, and then plus r of, and then these cycle through, so the next term would be r of eta, psi, eta, of nu, psi, eta, etc., is equal to all of this, where tau is the torsion map. Now, in general relativity, the torsion is assumed to vanish, so the entire right-hand side vanishes, and we get a really nice left-hand side. And a very nice form of the first Bianchi identity is simply that the left-hand side is vanishing. The second Bianchi identity takes this form, again, a cyclic sum of something to do with the Riemann, with the curvature map, is equal to 0. Here is the torsion involved. This term does not contain the torsion. This term, though, contains a covariant derivative. This one does not contain any covariant derivatives of the curvature. This one does. That equation turned out to be crucial for Einstein when he was looking for general relativity. He made use of it. Not in this form, but we will later see this equation in a different form where we can recognize what made it so important for Einstein. So again, if torsion is vanishing, the second Bianchi identity simplifies as well because this term drops out, and then we just have the cyclic sum of this vanishing. So how do those things look like explicitly in a chart? Especially when we choose for the tangent and cotangent spaces the basis vectors that come along with the coordinate system. How do these equations then look like? They have to turn into equations for the Riemann curvature tensor. So indeed, if we assume that there's no torsion, then these equations become much simpler. The right-hand side is vanishing, and here this term is vanishing. And these equations then simply become those equations. First Bianchi identity is the statement that the cyclic sum of these components of the Riemann curvature tensor vanish. And the second Bianchi identity says that this cyclic sum with a covariant derivative in here is vanishing. Just by spelling out what these expressions are, you arrive at that. There are more useful properties of the Riemann curvature tensor that one can prove. They're not Bianchi identities, but they're true anyway because of the definition of the Riemann curvature tensor. So in particular, we have that there is an antisymmetry in those 2 indices of the Riemann curvature tensor, and the last 2 indices. If you pull down the first index so that all are covariant indices, then we also have antisymmetry in the first 2 indices. And there's a symmetry in exchanging the first 2 to the last 2 indices. So if we just exchange those 2 with those 2, see here, that's a symmetry. And here are these equations written more abstractly, not choosing a basis. Actually, I think what would be nice is if maybe one of you volunteered to write up just a list of equations, of key equations, like the structure equations, Bianchi identities, symmetries of the Riemann curvature tensor or so. Let me know. If somebody has done that anyway, it might be good perhaps to make it available to everybody. It's just that, how do you remember all those details? It's good to have them all in one place, perhaps. Or maybe if I find the time, I'll do it myself and post it. Okay, so the Riemann curvature tensor, because it has so many symmetries and anti-symmetries, like these three, and the two Bianchi identities, the Riemann curvature tensor has a very particular property that helped Einstein a lot. Okay, it's back. It helped Einstein a lot. First of all, Einstein needed to write his equations of motion in terms of the energy momentum, in terms of the curvature tensor. And he needed to write the action in terms of the curvature tensor. So he needed to know what other tensors could be made out of the Riemann curvature tensor. And clearly, you can make other tensors out of a given tensor by contraction with another. Now, in general relativity, there's really not much you have available. You have the metric tensor, and you have the Riemann curvature tensor. And even the torsion tensor is absent. So the only tensors that you can combine to form new tensors in order to build and play around, build equations of motion, play around with possible structures of the theory, the only things he had available, It's still what?
It disappears and comes back. So
oh, you did?
Yeah.
Okay. I trust you there. Okay, so Einstein had not much to play with. So what he did is he took the Riemann curvature tensor with its 4 indices and then started contracting it with a metric to get something simpler. In particular, to get the candidate for the action from which then the equations of motion could be derived. And it turned out that because of all those symmetries and anti-symmetries, there's very little you can do with the Riemann curvature tensor without making it 0. So if you take the Riemann curvature tensor and you then contract this upper index with the second one of the lower indices, then you get the so-called Ricci tensor, which turned out to play a huge role in general relativity, as we will see. And then when you take the Ricci tensor and you contract that with the metric, the 2 indices of the metric, you get a scalar, the Ricci scalar. Both of these play an enormously important role in general relativity. And you may wonder, well, but how did Einstein guess right that you had to contract this index with that index first, and then contract the remaining 2 indices and so on? It seems arbitrary. It's not. It's the only thing he could do. If you do any other contraction, you get 0 because of the anti-symmetries that are in the Riemann curvature tensor. So the only non-trivial thing he could really have done was that there. That's the only scalar you can build from the Riemann curvature tensor. And the second Bianchi identity, it turns out, can also be rewritten in this way, using the Ricci tensor. Using that definition, the second Bianchi identity, remember, that's the one that involves the covariant derivative of the curvature tensor, can be written in this form, as you can verify in a few lines. And that's very important. When Einstein saw that, he knew he was up to something. That's because what we have here is a tensor with 2 indices. So it's a 2 tensor. In this case, it's written as a 1-1 tensor, one-fold contravariant, one-fold covariant. And you see that its contraction here with the covariant differentiation is vanishing. This looks almost like a conservation law, almost like a divergence is vanishing. And he knew that the energy momentum tensor had to have that property, that the energy momentum tensor, its covariant derivative had, when contracted, had to vanish. And here he had found a tensor made out of curvature that had that same property. And from that point, he started guessing correctly what the Einstein equation would be. We will get to that argument in more detail later on.
May I ask what the delta I star is?
Delta is just an II.
Oh, this one?
Oh, it's okay.
Yeah, so it's just a conical delta. Okay. Yeah, sorry if that looks like a star, it's okay. Okay, so in honor of Einstein, this particular combination then of the Ricci tensor and the Ricci scalar is called the Einstein tensor. You may know it, you may remember it in a slightly different way where there's a metric here. That's what you get when you lower that index using the metric. Then, well, it may just be that, yes, that's what it is. It's just a timeout because it was unplugged. Okay, sorry about that. Right. So the Einstein tensor obeys this equation here. As we will later see, this is what tipped off Einstein as to the right equation of motion. You know, Einstein and a colleague, Fokker, first cooked up a wrong theory of general relativity. And that was missing. That was the missing ingredient. Okay. So remember, we had two ways to specify the shape of a manifold so far. Either we specify a metric on a differentiable manifold that gives us infinitesimal distances and implied also finite distances, and that specifies the shape of the manifold. Alternatively, we saw that we can specify parallel transport. We can specify the covariant derivative, so how a vector changes as you parallel transport it infinitesimally. And that too, the non-triviality of parallel transport, described the shape of a manifold, both the curvature and the torsion. Now, the two ways of describing a manifold must be equivalent if they describe the same manifold. How can we connect the two? How can we relate the two? So let's say a manifold is specified by giving a metric. Then how can we find an affine connection that describes the same manifold? So how does a given G determine the gamma? The idea here is this. When you're given two tangent vectors at the same point, then using the metric, you can calculate the inner product. You can calculate basically their angle or their length. So you can calculate, if you take two tangent vectors, you can calculate using the metric the inner product. Using the affine connection, you can parallel transport those vectors. Now, during the parallel transport, they might be rotated, right? That's what curvature does. It will rotate a vector even though it's parallel transported. But if you take two vectors and you parallel transport them, even though they might be rotated, well, they're both rotated the same way because they're both parallel transported on the same manifold along the same path. So their angle and their length, their angles and lengths should not change. So what links parallel transport to metric information is the requirement that the length and angles of vectors should not change under parallel transport. In equations, it means this. Consider a path in the manifold and any two vector fields, eta and nu, that are parallel transported along gamma. So eta is autoparallel to gamma, and nu is autoparallel to gamma, which means that if you go along the path gamma, and you check out the vector field eta, you find its vectors are parallel transported versions of another. And also the vector field nu has the property that its vectors on the path gamma are parallel translates of another. So it's this situation. There's nu, there's eta, there's nu, and they're parallel transported along So we have that the vector field eta covariantly differentiated in the direction of the path, so in the direction of the tangent vector of the path, is vanishing. And the autoparallel condition on the vector field nu is the same thing. It covariantly differentiated in the direction of the path is vanishing. Then what we require is that if you take the inner product now between the vector field eta and the vector field nu at a point or at points on the path, then you get a certain number. And how do you do that? Take a vector field, and the metric to contract them. You get a certain number. That number is not supposed to change. D by dt is equal to 0. It's not supposed to change as you travel along the manifold. This is the mathematical statement of the idea that vectors rotate or are parallel transported in such a way that their length and relative angles don't change. Okay, so this is now the key equation that relates the metric to parallel transport. Explicitly, if we write it out in a coordinate system, it is this. So we covariantly differentiate in the direction of the path. So we covariantly differentiate in the direction of the tangent vector. This expression here, which is the inner product of two tangent vectors taken with respect to the metric. We do know that the Leibniz rule holds. So the covariant derivative will produce three terms. The covariant derivative will be taken on this, leaving those two vectors the same, plus there will be a covariant derivative acting on this, leaving the rest the same, and there will be a term where the covariant derivative is acting on that vector field, leaving everything the same. And here are those three terms. The direction vector of the covariant derivative always stays in front. This first term has the metric covariantly differentiated, the second term has eta covariantly differentiated, the third term has mu covariantly differentiated. Now, the second and the third term vanish because you see the contraction of this with that covariant derivative is the covariant derivative of the vector field in the direction of the path. But that's vanishing because we assume that our vector fields are parallelly transported. So because they are parallel transported, the second and third terms are vanishing. And therefore, it's the first term that is the only one to survive. And we obtain the equation that 0 equal to the first term, 0 equal to this, where we have the covariant derivative of the metric. Now this ought to hold true everywhere on the manifold for all direction paths. So it should be true for any gamma dot, any eta, any nu, anywhere on the manifold. But that means that this expression itself has to vanish. In other words, the covariant derivative of the metric in any arbitrary direction has to vanish. And you see how this is linking the metric description of the manifold to the description of the manifold, or the shape of the manifold, through an affine connection, because it links the affine connection to the metric. Now, is there actually an affine connection for any given metric that will do the trick? Indeed, that's the fundamental theorem of pseudo-Riemannian geometry. It says that for every pseudo-Riemannian manifold given by a differentiable manifold plus a metric, there exists a unique affine connection that is torsionless. We want that for general relativity, and that is compatible with the metric in the sense that the parallel transport is leaving the relative angles and lengths of vectors invariant. That affine connection is called the Levi-Civita connection. More generally, if you start with any differentiable manifold and a metric, and you also have a tensor field that is antisymmetric in two lower indices and has one contravariant index, then there always exists a metric preserving affine connection for which this is the torsion tensor. Not that we need it for general relativity, but just for completeness, let's state that. Well, how do we get that? Explicitly. Assume that we know the metric, and now we want to know what this affine connection that belongs to it actually is. Well, the fact that the covariant derivative of the metric is vanishing is, of course, just this equation. Remember that the covariant derivative of a rank 2 tensor is given by three terms: the ordinary derivative of that rank 2 tensor, of this twofold covariant tensor, and then we get two terms because we have two indices in the metric, mu and nu. There's the Christoffel symbols here, and they're minus signs because the indices are lower indices. If we did it for the metric with the upper indices, we would have pluses there. I'm writing down this equation 3 times. This is the same equation as that one, same as that one. The only thing I did is I switched the indices around. I renamed them cyclically. See, this term becomes that term if you cycle the indices. If you make the alpha the first index, the mu the second, the nu the third index in this. And I did the same thing for the other terms, and here I cycled them yet again. So it's 3 times the same equation. And then let's call those equations 1, 2, and 3. Let us take 1/2 of minus the first equation plus the second plus the third. Einstein already did that, and Riemann, I suppose, did this. What you obtain then is a nice cancellation of the terms that involve gamma, and you obtain just one term that involves gamma, and it is equal to all those expressions in terms of the metric's derivatives. We can shuffle that metric tensor on this side as well, simply because we know it's non-degenerate. There is an inverse to that matrix. And so we now obtain the Levi-Civita connection in terms of the metric. Okay, so now we have it all concretely in terms of coordinates. Today is the last day we do really just the mathy part of it, of general relativity. But we'll have to do a bit of an upgrade yet again. Okay, so this may be a little rough again, but hold on, general relativity is coming. Okay, so we upgrade the math. I anticipated it earlier. What we will do is we will now free ourselves from the usual choice of bases that comes with the coordinate systems, and we look at what happens if we freely choose the bases in the tangent and cotangent spaces. So let's say we choose a basis EI in the tangent space and a dual basis theta I of cotangent vectors theta I in the cotangent spaces. That's one thing we will do. And I anticipated that already earlier. We know why that's going to be useful. The second thing we'll do today is we will allow our differential forms to be not only number valued, but also tensor valued. You see, a differential form is ordinarily number valued in the sense that if you feed it with sufficiently many tangent vectors, let's say if you have a P form and you feed it P tangent vectors, then they all evaluate into a number at every point of the manifold. Now, we will allow differential forms that are more general. A differential P form, which when you feed it with P tangent vectors, gives you a tensor, not just a number, not just a function, but a tensor or tensor field. This is useful for several reasons, one of them being that, remember, differential forms can be integrated. And in this way, you can integrate also tensor-valued things. Well, and in particular, this would allow us to see the Bianchi identities in a simpler, more transparent way. Okay, so for now, we will not assume that the affine connection and the metric are related to each other. They can still be arbitrary. And also we will allow, because why not, we will allow the torsion to be not zero. Okay, so we start with the first innovation that I talked about, namely choosing the basis arbitrarily. The definition is that a moving frame is a set of tangent vectors of contravariant vector fields which are chosen such that at every point of the manifold they form a basis of the tangent space. Okay, so in order to specify a moving frame, you have to specify for every point of the manifold n, if the dimension of the manifold is n tangent vectors. And here they are, n tangent vectors. No, they're functions of x. For every point on the manifold, you get another tangent vector. So what this is a bunch of tangent vectors, n tangent vector fields. The main requirement on them is that it's not a degenerate set. At every point of the manifold, they've got to be linearly independent. And then we define the dual basis that belongs to this basis here. The dual basis in the cotangent space is defined as those cotangent vectors which evaluate on these basis vectors into the Kronecker delta. A bit of terminology. In the case of space-time, we have 4 of them, because space-time is 3 + 1 dimensional. The 4 of them. And then such a moving frame is also called traditionally, and this may go back to Einstein, a Vierbein, which is a German word that means 4 legs. Because each tangent vector you can think of as a leg, and there are 4 of them pointing in 4 dimensions. And another term for that is tetrad, where I think that goes back to the Greek root. In more general dimensions other than 4, such a frame is also called a Vielbein instead of Vierbein. The only change is that the R goes into an L, and Viel means in German many. It just means many legs. Okay, so what we have is that each, actually we will usually work more with the cotangent basis vectors than with the tangent vectors. But, you know, it's a matter of convenience really. But the point is where we tend to use, the reason why we will work more with the basis of the cotangent vectors than the tangent vectors is that the cotangent vectors are also one forms, and therefore differential forms, and therefore you can do all sorts of things with them, like taking the exterior derivative, like taking wedge products of them, and so on. That's why these are a little bit more useful than the basis of the EI. Okay, so each covector field, theta I of x, is a one form. And in particular, this means that if you take the D of it, then you get a 2 form, because the D of any P form is a P + 1 form. The combination of a cotangent vector field with its corresponding dual tangent vector field can also be collected into what is called a frame, which is just a combination of the theta I and the EI. And that is a 1-0 tensor valued 1 form. You can also view it simply as a 1-1 tensor, right? One-fold covariant, one-fold contravariant. But the covariant part can also be viewed as a 1 form. So you can view this now as a 1-0 tensor valued 1 form. Let me remark that if you choose your basis in the conventional way, I mean, you could say, well, I appreciate the freedom you give me to choose my basis vectors whichever way I want. Thank you very much. But I like this basis, the one that comes with the coordinate system. If you do that, then sometimes you actually get a benefit of some simplification. For example, the d theta I is then dd of xi being the coordinate function. So you get that d theta I is equal to 0 in this case. In general, though, that won't be true. If you choose an arbitrary set of cotangent of basis vectors in the cotangent space, then they are not the d of something, and so in general they will have a non-trivial exterior derivative. This will generally not be 0. It's only 0 if you choose the basis very specially. Now, for whichever choice you make, and that's very important, whichever choice you make of basis in your cotangent spaces, this basis can always be expanded with suitable expansion coefficients in terms of the basis that comes in with a coordinate system. That's very useful because this basis is given for free with a coordinate system. So we have it anyway. And that basis may be much more useful for practical applications. So here is how we move from the basis that we get for free to the designer basis that we may design in such a way to have particularly nice properties. Now, since these form a basis of the cotangent space and these form a basis of the cotangent space, it's really trivial that there's got to be a matrix of change of basis between the two. And that change of basis matrix will in general be dependent on where you are on the manifold, so it's a matrix lambda of x. Notice that the lambda ij of x are just coefficient functions, right? They're just functions. These are cotangent vectors, these are cotangent vectors, and these are 0 forms. They are functions, just coefficient functions. Now, remember that in general, as we just discussed, in general, the d, the exterior derivative of those theta, is not going to vanish. The d applied to these will vanish, but the d applied to that will not vanish. And that means that when you calculate the d of such frame vectors, such a basis, then you will get a 2 form, and every 2 form is a linear combination of this basis in the space of 2 forms, right? The wedge product of the theta j and theta k span, of course, the space of 2 forms, and so there must exist some coefficient matrix that relates, that expresses the 2 form that you obtained by taking the exterior derivative of this basis in terms of that basis of the space of 2 forms. And you can calculate, if you're given that, so you've chosen a coordinate system, got this for free, and then you've made an additional designer choice of your choice of basis vectors in a tangent space, so you've chosen these functions lambda. Once you've done that, you can calculate what d theta is. And therefore, you can calculate now what these coefficients c are. And I invite you to do this little calculation. Express the coefficient c in terms of those coefficients lambda. So again, basis vector in the space of 1 forms. Together, they form basis vectors in the space of 2 forms. That's a 2 form, and these are coefficient functions. Clearly, this C matrix is antisymmetric in J and K because this piece is antisymmetric in J and K. Well, more precisely, you could choose to put something symmetric in there too, but it wouldn't change the equation because it would be contracted out with the antisymmetric part here. Okay. So now that we've allowed ourselves to choose arbitrary bases in the tangent and cotangent spaces, as long as they are dual bases to each other, we can now express the torsion tensor, the curvature tensor, the metric, and the Christoffel symbols in those designer bases. And we do it in exactly the same way as we've done all along. Here's the torsion tensor. Well, it's the coefficient matrix function of the torsion tensor. It's by definition simply what you get when you take the torsion map and you plug in two tangent vectors, two basis vectors, and you evaluate with a basis vector here. That's how you get the coefficients. Previously, we did this with a particular choice of basis. We put in here the d by dxk, the d by dxl, and the dxi. Now we allow ourselves to use the arbitrary basis that we choose. And the same for the curvature, same for the metric, and the same for the Christoffel symbols. We define them now, we define those coefficient matrices with respect to our designer basis. Now, when we change coordinate system, how are these coefficient matrices going to change? Not at all, right? Remember that if we change coordinate system, then, well, you're changing coordinate system, but you're not changing automatically what your basis is, what your choice of basis is in the tangent and cotangent spaces. We've made our choice. We've made our designer choice. We take the e's, we take the thetas. They are our basis vectors for the tangent and cotangent spaces, and therefore we can calculate those matrices here, and whatever coordinates we choose doesn't matter at all. Okay? They don't transform in any way. A tensor is a tensor. It's just like a vector is a vector in a Hilbert space or in a vector space, and you may represent it with different coefficients depending on which basis you choose, but it's still the same vector. And similarly with the tensor. It's always the same tensor. And you only get different representations when you choose different bases in the tensor space to represent it. But if you hold the basis fixed, like we've now committed to a basis theta and e, then that is what determines your coefficients. That's the only thing that determines the coefficients. If you change coordinates, it doesn't matter. See, only if you choose for your e's and thetas the canonical basis that comes with the coordinates, and you change coordinates, and then you change allegiance, and you choose your basis vectors again as those that come with the coordinates, then you have a change of bases in the tangent and cotangent space as you go along with a change of coordinates, and then of course the coefficient matrices will change. But in general, these two things have nothing to do with each other, change of coordinates and change of bases in the tangent and cotangent spaces. So let us now consider an arbitrary change of frame. You can change frame even when not changing coordinates, right? So you keep your chart the same, but you may change your mind about which basis you want to choose in the tangent and cotangent space. So we might have initially worked with this basis. Now we prefer the theta bar basis. And they will be related by some coefficient matrix aij of x. And correspondingly, because we want the E bar basis to stay dual to the theta bar basis, this automatically implies that the E's must transform into the E bars using the inverse of the A matrix. Okay, so in this case, we are changing frame without changing coordinates. or with changing coordinates. It has just nothing to do with choices of coordinates. Okay, so what this means is that our coefficient functions, when we represent tensors in terms of bases in a tensor space, the coefficient functions do no longer transform. As long as we stick to one basis in the tangent and cotangent spaces, they don't transform under change of coordinates. Now, let's get back to this other ingredient, the math upgrade that we are considering today. Tensor-valued p-forms. Remember, ordinary p-forms have p slots to plug tangent vectors in. If you do that, you get out a number at every point in the manifold. A tensor-valued p-form also has p slots for tangent vectors, and if you plug p tangent vectors in there, you don't get out a number in this case, you get a tensor at every point. So the definition is that an RS tensor-valued p-form phi is, in particular, an antisymmetric p-multilinear mapping, in other words, a differential form, at each point of the manifold, which is such that it takes p tangent vectors as inputs, and it outputs an RS tensor. Now, if you choose to contract these R contravariant and S covariant indices with basis vectors, so you contract the R, I mean, this is R slots to put in cotangent vectors. This is S slots to put in tangent vectors. If you put them in, the basis vectors, then you obtain numbers again. So your differential form is now number valued again. Because, I mean, in principle, it's RS tensor valued, but an RS tensor has so many inputs. If you satisfy them, if you put tangent and cotangent vectors in there, then you get a number again. And those numbers are then called the coefficient p-forms. So if you take this RS tensor and you fill it regarding its RS covariant structure with basis vectors, then you get, again, number valued outputs, and these are the component p-forms. For each choice of basis vectors here and there, you get a component p-form. These are literally the components of the tensor. You can view an RS tensor as a giant matrix, which has R upper indices as lower indices, and each entry of this multidimensional matrix is a coefficient p-form. This covers a lot of ground. So in particular, it covers what we used to think of as RS tensors. An ordinary RS tensor is also an RS tensor valued p-form. It's simply an RS tensor valued zero form. You see, an RS tensor doesn't have, it's not a differential form per se. It doesn't have slots to put tangent vectors in there in an antisymmetric way. But zero forms are just functions. They don't have any input slots. So in particular, an RS tensor is like that. So RS tensors can be viewed also as zero forms, which take values in the RS tensors. And vice versa. Consider now a p-form, an ordinary differential p-form of the kind that we've considered all along. They can also be viewed as tensor-valued p-forms, namely as 0, 0 tensor-valued p-forms. You know, number or function-valued p-forms. So this definition covers both regular RS tensors, namely as zero forms. It also covers regular differential p-forms as 0, 0 valued p-forms. But it's more general than that. And the reason why we introduce this is that the torsion and the curvature in particular, but also Christoffel symbols and so on, have that structure. Even the metric has this structure. Consider the torsion 2 form. Remember the torsion tensor, or the torsion map in this case, is antisymmetric. The torsion tensor has one contravariant upper index, and it has two covariant lower indices. And if you remember, the torsion tensor is antisymmetric in the two lower indices. What this means is that we can view the torsion tensor as a differential form with regards to its two lower indices, because they are antisymmetric. And then we are left with one upper index. So the torsion tensor, therefore, is a two-form, all right, because it has two antisymmetric lower indices, but it's not a number-valued two-form. It's a 1-0 tensor-valued two-form because of its remaining one upper index. Okay, so this 1-0 tensor-valued two-form can be defined through its action on two vector fields, psi and eta, which are the ones that we put into the two-form. So this is going to be the notation for the 1-0 tensor-valued torsion two-form. You plug in two tangent vectors to satisfy the two forms open slots, and then you're left with one contravariant structure, and this is this coefficient function theta I contracted with the basis vectors in the space of tangent vectors. So here you have the structure of plugging in two tangent vectors and getting out one tangent vector. This is what the torsion map did. You plug in two tangent vectors, and then you get out a tangent vector. That's what the torsion map did, in such a way that it's antisymmetric in those two arguments. So this is also antisymmetric in those two arguments, and that is what allows us to view the torsion as a two-form, a 1-0 tensor-valued two-form. Given a frame, given a choice of designer basis, we know that we can view the torsion two-form, which is a 1-0 valued two-form, and we can write it always in this way. Here we have a basis in the space of two forms, and then we have a coefficient function which contracts with those two indices and has one remaining upper index for the output, which is tangent vector valued. We can do the very same thing with the curvature. Curvature map is also antisymmetric. However, the curvature has one more index. The curvature is a two-form again because of this antisymmetry in those two lower indices. But the curvature has two indices left over, an upper and a lower index left over. And so the curvature gives us a 1-1 tensor-valued two-form. So if you apply the curvature map, then what do? You feed it two tangent vectors and apply it to a third tangent vector, and you get out a tangent vector. Overall, what we have is that the curvature two-form takes two tangent vectors as input to satisfy its two-form structure, and then as output is left one upper index, one lower index. If we contract that upper index here, we obtain a tangent vector as the output of all of this. This whole structure of that is a tangent vector, and that's what the curvature map did as well. It maps three tangent vectors into a tangent vector. Okay, now let's choose a frame again. If we choose a frame, then a basis in the space of two forms is again given by this. And there must be coefficients, and here they are. The Riemann curvature tensor contracted with respect to those two indices, which, if you remember, are antisymmetric. And then we are left with those two indices, upper and the lower one. This is a definition for convenience or for tradition. And then here we obtain the curvature 2 form. So the curvature 2 form has only two indices, unlike the Riemann curvature tensor, which has four indices. Two indices are suppressed because they are now considered to make it into a differential form. They're suppressed because it's a differential form. It's a 2 form, and for the 2 form, we don't write out the indices explicitly. So we really haven't done anything in particular. We've just changed perspective here. We've just declared that in the Riemann curvature tensor, just like in the torsion tensor earlier, there are two lower indices that are antisymmetric. That means that we can view this tensor in particular as a differential 2 form. And because there are indices left over, we have to make it a tensor-valued 2 form. In this case, a 1-1 tensor-valued 2 form. But you see, the change of perspective is valuable because we know that we can integrate differential forms. And we have more tools for differential forms than we have for regular tensors. We have in particular the exterior derivative and things like that. Now how about the connection? The affine connection. Is that a differential form? This is a non-trivial thing now because, see, the Christoffel symbols are defined in this way. If you choose some designer frame and defined in this way, it's the affine connection for your choice of basis vectors. And the Christoffel symbols are not tensors to start with. And also, the Christoffel symbol is not antisymmetric in those two indices. If the Christoffel symbol were antisymmetric in those two indices, then you would have a weird kind of physics. No curvature, only torsion. And we know that torsion is already a tensor, right? So, and is also a 1-0 tensor valued 2 form. So that's not the issue. We don't care about the antisymmetric part again. That's torsion. That's taken care of already. No, we're interested in the symmetric part. So it doesn't seem like this can be viewed as a differential form that takes values in something non-trivial. We were able to do it for the torsion tensor because it had two indices that were antisymmetric. For the curvature tensor because it had two indices that were antisymmetric. But this doesn't have indices that are antisymmetric. Still, it turns out to make sense to view this as a 1 form. We'll later see exactly what that gives us, but let me explain why we can do it. It's because a 1 form is not antisymmetric in anything. A 1 form as a tensor simply has a lower index. So what we can do is we can simply grab one index there and say, well, that's a 1 form. We view it as a 1 form. And then the remainder is not going to be a tensor. So it's not going to be a tensor-valued 1 form. It's going to be a something-valued 1 form. We will later find out where it takes its values in. But nothing prevents us from saying it's a something-valued 1 form, because this is a lower index. Okay? So that's what we will do. We will define the connection 1 forms in the following way. We will say, okay, we grab this index here, the k, we contract it with a basis of 1 forms, and then we are left with two indices. So the omega ij, again, has one index suppressed, just like the Riemann curvature tensor. Out of its 4 indices, had 2 indices suppressed because we regarded them now as 2 form. Now the connection 1 form has only 2 indices left, and 1 index is suppressed under the hood. It's still there, but not notationally. We don't express it anymore because we now view it as a 1 form with respect to that. Physically speaking, this makes sense because the connection 1 form really has one open slot that's asking for a tangent vector. It's because the connection is a directional derivative, and you have to give the direction. You have to give the tangent vector that goes in there. That's what makes the connection one form a one form. It's a one form that asks for a tangent vector to tell it which the direction is in which it is to differentiate. Okay, so you see, we just take the Christoffel symbols and then contract them with the bases, and there you go, you have the connection one form. So what we can then write, using this definition, we can write that the covariant derivative of a tangent vector in the direction of psi, which would normally be written as a Christoffel symbol and the psi contracted there, can now be written as, well, feed the direction vector into the one form, okay? And then you have two indices left over, and that matrix is what rotates that tangent vector into, this matrix gives, applied to that tangent vector tells you how that tangent vector is changing direction as you parallel transport. Now, this is the covariant, this is in the new notation, this is how the covariant derivative acts on tangent vectors. Let us also figure out how it acts on cotangent vectors. Once we know that, we can work out how it acts on all tensors. The proposition here is that the covariant derivative acts on covectors in the following way. So acting on a tangent vector gives us this. Acting on a cotangent vector gives us that, with a minus sign here. So again, you plug the direction vector into the one form, into the connection one form, you get a matrix, and that matrix transforms the tangent vector into the vector that indicates how much a vector changes under parallel transport. Let's prove that quickly. The theta and the e are dual bases. So if we evaluate them on each other, we just get the Kronecker delta. The covariant derivative of the Kronecker delta, well, is 0. And so we have that 0 is equal to the covariant derivative of the left factor, and by the product rule, plus this evaluation with the covariant derivative on the right factor. Remember that it doesn't matter whether you first covariant differentiate and then evaluate tensors on each other, or contract indices, or whether you first contract indices and then covariant differentiate. So that's what we're using here. So we have 0 equal to this term plus that term. We do know how this action plays out because we have it up here. Okay, covariant derivative of a tangent vector, we know that. Covariant derivative of a tangent vector, plug it in there, and therefore we can solve this equation now for that. And you see how the minus sign arises. We have to put this on the other side. And so we obtain that so we obtain that 0 is equal to this plus that, where I've just plugged in the connection form for this outcome here. Just plugged in this equation over here to obtain that. Now, bringing that on the other side, we obtain what the proposition said. Okay, so now we can calculate covariant derivatives of basis vectors in the tangent and cotangent spaces. And that's going to be useful, of course, once we shift to working in the designer basis all the time, because things will be expressed as linear combinations of those.
This is only true for the Relativity connection, right?
Yes, we did. Yes. Yes. Now, yeah, because otherwise, you see, it wouldn't even be well defined, because it would make a difference in here whether we contract with the k or whether we contract with the j, because it wouldn't be symmetric. See, if it's symmetric, if there's no torsion, then yeah. Okay. Now, the connection one forms are not tensorial, because the Christoffel symbols are not tensors to start with. So how do they transform? Now, they don't transform at all if you change coordinates. They transform if you change bases in the tangent and cotangent spaces. Let's see how they do. So let's say we change from one designer basis to another designer basis with such a change of basis matrix. Then the proposition is that the connection 1 form changes such that the coefficient matrix is expressed in terms of the old coefficient matrix omega in this way. You can probably see how, in the case where theta and theta bar are the canonical bases that come with a change with coordinate systems that you change, in that case, this reduces to the equation that we had before for the transformation behavior of Christoffel symbols. But now we don't have our choice of bases tied to any coordinate system. We can change coordinate system without changing bases, or change bases without changing coordinate system. So what really matters for those tensors here is, for the coefficient matrices, is of course the change of bases. And if you do an arbitrary change of bases in the tangent and cotangent spaces, this is how they transform. I leave you to read the proof on your own. It's a nice little exercise. I gave a lot of explanations for why the one and the other thing works out. But again, we can tell that this is not tensorial because of this extra term that doesn't depend on omega at all, which means that omega bar might be non-zero even if omega starts out being 0. Right? Even if omega is 0, so in one basis there is no omega. In the other basis, you might have that even though this term is absent, that term contributes because there's a dA. And yeah, the physics of that is, of course, pseudo-forces. Now, we introduce a last derivative. I hope it's the last one. Yeah, I think it's the last derivative, derivation that we introduced. It's the absolute exterior differential D. And it is the derivative that applies to tensor value differential forms. So the most general thing, right? Tensor value differential forms generalize both differential forms and tensors. And we have the covariant derivative acting, the absolute covariant derivative acting on tensors. We have the exterior derivative acting canonically on differential forms. The capital D does both. It does this for the tensor part of a tensor value differential form, and it does that for the form part of a differential of a tensor value differential form. So the proposition is that for every RS tensor valued P form phi, there exists a unique RS tensor valued P plus 1 form d phi, whose components relative to our designer basis are given in this way. So you see the capital D is going to do the job of a covariant derivative on the tensor part, and that doesn't change the character of the tensor part. But it also does the exterior derivative action on the differential form part, and that turns a P form into a P plus 1 form. So overall, when you apply the absolute exterior derivative on a tensor valued P form, then when you write it out in explicitly, then where the tensor part is spelled out in our designer basis, then this is what you obtain. Let me guide you through this long formula there a bit. Okay, so phi is a tensor valued differential form. This is the index structure that arises because it's a tensor valued differential form. The indices that belong to its differential form character are suppressed again. So the action of the capital D is to apply the exterior derivative, the ordinary exterior derivative, to those coefficient forms. Right? So if you choose your basis vectors, you feed them into the tensor structure, then you get just an ordinary form again, and you can apply the exterior derivative to that. Plus, you apply the connection one form to all of the contravariant and covariant indices of the tensor structure of it. What this means is that if your tensor valued differential form, for example, is trivially tensor valued, let's say it's 0, 0 tensor valued. In this case, there are no indices up here. It's just an ordinary differential form. It's 0, 0 tensor valued. In this case, we only have this first term. It's just the ordinary exterior derivative on that differential form. And these terms are all absent because this connection one form doesn't even have indices to contract with, because this thing doesn't start out being tensor valued. None of these terms. On the other hand, if our tensor valued differential form is a tensor valued differential zero form, if it's really just an RS tensor, then the D has nothing to act on except for the scalar part of it, which means that it will just do the ordinary derivative. And then we have all those terms which are, if you spell it out in Christoffel symbols again, just what you need for covariant derivative, right? Ordinary derivative on a function, and then here the Christoffel symbols. That's what it boils down to. But if the phi in question is both tensor valued and a differential form, a non-trivial differential form, then we have contributions from both. Since the torsion and the curvature tensor are tensor value differential two forms, it is convenient to introduce that notation here. It turns out that D is an anti-derivation. You see, there's a minus sign depending, as always for differential forms, there is or is not a minus sign depending on the degree of the differential form. If the phi and psi in question are not actually non-trivial differential forms, if they're just zero forms, if they're just ordinary tensors, then this is just the ordinary product of tensors because they are zero forms. The wedge product is just the ordinary product. And then there's also no minus sign because if P is 0 for zero forms, then it's minus 1 to the power 0 is 1. So it's an ordinary derivation for ordinary tensors. But for tensor value differential forms, in general, it's an anti-derivation. For special cases, an ordinary P form is 0, 0 tensor valued, is a 0, 0 tensor valued P form. And in this case, as I explained already, the capital D is D. On the other hand, if what we're dealing with is an ordinary tensor, then it's a zero form, so the capital D then is just the covariant derivative. Remember the absolute covariant derivative without specification of the direction in which we differentiate. So how are now our key players in on that stage related? How is the connection one form, the metric, the torsion and the curvature, two forms? How are they related now? Well, here's a proposition. The affine connection is now metric if and only if the absolute covariant derivative, the absolute exterior derivative of the metric is vanishing. That's not such a big deal to say that because the metric tensor is really a zero form. I mean, it's a 0, 2 tensor valued zero form. And so this is just the ordinary covariant derivative. So the claim is simply that the covariant derivative of the metric is equal to 0, but that's what we knew from earlier. That's what makes a Levi-Civita connection. That, namely, the fact that the requirement that the covariant derivative of the metric is vanishing is to require the compatibility between affine connection and metric. And that translates in this language simply into that statement here. Right? This is exactly the covariant derivative of the metric. This is just the ordinary partial derivative. This gives us the ordinary partial derivative, and this gives us the Christoffel symbols, because that is just the Christoffel symbols with one index suppressed. Further, in this new language, we get the famous so-called Cartan structure equations. And they are saying that the torsion tensor, or the torsion two-form, which is a 1-0 tensor valued two-form, has this form here in terms of our designer basis and the connection one form, and the curvature two form, a 1-1 tensor valued two form, is given by this expression. This is just a fancy way to express something that you've known for a long time, namely that the torsion tensor is just the antisymmetric part of the Christoffel symbols. If you choose the theta to be the basis that comes along with the coordinate system, then that term drops out because the theta is dxi. Then you have vd, which is 0, right? So that drops out. And here you have, because of the wedge product, an antisymmetric term, just gives you this. That boils down just to that. This is just more powerful because it's much more general. You can choose any arbitrary basis now. Well, yes, you might get some more complications because this might not vanish, but it's much more powerful because you're not tied to a coordinate system. Similarly, here, the metric tensor, the curvature tensor. Curvature tensor is expressed in this way. That's just a fancy way of writing what you've known for a long time, namely that the Riemann curvature tensor is, the difference between two Christoffel symbols differentiated, and then quadratic terms in the Christoffel symbols. Let's look at this. What we have here is that this just gives us ordinary derivatives of the connection one form, which is derivatives of the Christoffel symbol, the first two terms. And then here we have Christoffel times Christoffel. That's this stuff. If you specialize to the case of the basis that comes along with the coordinate system. Again, I will skip the proof of this. It's a little tedious, but all details are there, and it's instructive to go through that proof. So what's the use then of these Cartan structure equations? Now, with the Cartan structure equations, we can now re-express the Bianchi identities in a more simple way. Remember, the Bianchi identities used to involve this cyclic sum of terms, and it was really a little tedious. Now, the first Bianchi identity simply takes this form. The capital D, the absolute exterior derivative of the torsion two form, is given by this curvature tensor, wedge, designer basis. And the absolute exterior derivative of the curvature 1-1 tensor value 2 form is vanishing. That's the second Bianchi identity. That's the one that involves covariant derivatives of the curvature tensor, if you remember. This one doesn't involve derivatives of the curvature tensor, but that one does. In the case of general relativity, things simplify a little bit more because we assume there that the torsion is absent. So therefore, this is 0, which means that whenever that expression comes up, we know it's 0. Yep?
So, for like sufficiently nice manifolds, do we have results similar to like closed being if and only if exact, or something like the second Bianchi identity here?
Oh, for the D?
Yeah.
No, not really. It's not generally true that D squared is equal to 0. No, you don't even have that. So you don't have that if a tensor valued P form is the D of some other tensor valued P minus 1 form, that then the D of it is vanishing. The tensor valued part of it can screw that up. Because you get extra terms from the covariant differentiation. Right, so the Bianchi identities, therefore, in the case of general relativity, reduce to these equations. And they are easier to remember, I guess, than the cyclic permutations things that we had earlier. So again, curvature 2 form, wedge designer basis is equal to 0. And here we have that the d of the curvature 2 form is vanishing. Now, just to make sure, just to wrap this up, what happens when we allow ourselves to choose designer bases? It comes with advantages and disadvantages. Let us now look, for example, at that calculation again of the Christoffel symbols in terms of the metric. We did that calculation, if you remember, by writing down the same equation 3 times and then doing some suitable cancellations between them and so on. We did that at the time, choosing as the basis that comes along with the coordinate system for convenience. What if we allow ourselves to choose arbitrary designer bases to do this? We can still go through the same calculations, but we actually pick up extra terms. Let's see. So if we go with the, in the case of arbitrary bases in the tangent and cotangent spaces, we can calculate that the Christoffel symbol now is no longer simply given by this expression, which would be the expression if you choose your basis along with the coordinate system. I mean, as the one that comes with the coordinate system. No, now we have these additional terms. Remember what the C's are? The C are telling you you have the theta I, that's your basis in the cotangent space. And then if you take the d of that, then this is, I think that was a minus 1/2, and then ci jk, and then the basis of the c j wedge k, right? And if you choose for the theta, for your basis in the tangent space, the dxi, well, then the d of that is equal to 0, and we had that the c is equal to 0. So if we choose the basis that comes with the coordinate system, then the first line goes away because this matrix C is absent. It only arises if we allow ourselves non-trivial choices of bases here. So that seems like a price is to be paid here. And then, oh, it's here. Yes, okay, right. Okay, so that's that. But then this propagates. If we go and express now the Riemann curvature tensor in terms of Christoffel symbols, then what we get is, in a designer basis, the usual expressions, namely linear in gamma, but differentiated, plus square in gamma, squared in gamma. That's the usual expression here in green. But then we also get this additional term that only arises if we have a non-trivial choice of basis here. But nevertheless, it will be worth it, in particular because choosing the designer basis suitably, we can, for example, make the metric always, everywhere. Look, the metric tensor will have a coefficient matrix that is always just the one of special relativity. And all the non-triviality will now be in the C's. And that will allow us, in particular, for example, to write down the Dirac equation. It would be hideously complicated if we didn't choose the basis in this way. But I wanted to point out that you get extra terms when you choose the designer basis. On the other hand, if you now change coordinate system, this matrix and that matrix don't change at all, right? Because you've now chosen your basis to be the theta, independently of what coordinate system. So they no longer transform at all. Okay, right. So that is all about the math. I think we have only very little math things to cover in this course. It will be all applications now. On Friday we will do spectral geometry, which I hope you will like. It's about hearing, shape, and so on. It has also to do with my own research. And then we fully launch into general relativity. Okay? See you on Friday.